All right, this is Professor Cummings, and this is Module 7, Class 7 for Design for Manufacturing Assembly. And in this particular class, we're going to be going over alternative manufacturing processes. So what we've done up to now is looked at the different impacts or the different influences that design can have on the manufacturing and assembly processes. So we've looked at things such as your tolerances and your surface finishes, what those can have an influence over. You've looked at material selection. Now we know that this dictates a major portion of your manufacturing cost is based on the material that you select. And then things such as the theoretical minimum part count, total parts being designed and are purchased into a component, and being able to design those deliberately so that you're creating a more efficient part, making it easier to assemble, easier to manufacture, as well as just making a overall easier to handle component. Now we looked at those things that you can actually impact during the design stages, and when you're not doing an over-the-wall design process or over-the-wall design method, what you actually end up influencing are things such as the cycle time. How long does it take to machine that component? How long does it take to actually assemble that component? Do your tolerances have some sort of impact? Tolerances of surface finish have some sort of impact on how much the cycle time happens. Your outsourcing processes. Did you end up impacting or causing some sort of process, specialized process that needs to be used? Your part flow. Did you cause this part to have to be, or your components have to go through several different processes, have to backtrack, get reheat treated, reground, and remachined? Do these things impact your assembly efficiency? As well as then all of them seem to have some level of play in how much machining you're going to work or other manufacturing processes, as well as your specialized work holdings. So just overall design such as geometries, part count, surface finish, material selection have all sorts of impact down the road in your throughout your manufacturing assembly process, and we tried to cover how that happens. Now, what are we looking at in this section? The objectives is to look at machining limitations. Now, this project that you have for this class has been primarily a machining project. There has been some grinding, there's been assembly for design for manufacturing assembly, but the machining process that we've looked at has been machining primarily. So we're looking at if we could minimize some of the machining, what other alternative process could we use? And what we're going to do is give a brief overview of these particular processes. Now, they're not going to be in depth. It's going to be a very basic overview. If you're going to include this into your project and write up in your final paper as you modify the design of the machine that I gave you, you're going to have to do some extra research, to go in further depth. But, I'm going to give you an overview, introduce you to some processes that you may or may not have been familiar with, as well as some of the pros and cons behind them. So again, the goal of this section, what I want you to take away from this module, before your final project is actually due, alternate manufacturing processes, that we didn't discuss before. So now you've got a bigger toolbox that you can work with. What I'm going to do is go over some of the advantages, some of the disadvantages, and then I'm going to give you some examples, some applications of these alternative processes and why you would even want to use them. So we went through, you've seen this pyramid before. If we just look at where machining lands in the pyramid of manufacturing and design, and assembly process. So you've got, it falls as a secondary process, which means that the primary geometries have already been selected. And now you're finishing up those geometries and sending it off to as a more finished component to be assembled. It's one of the more common manufacturing methods. It's suitable for high and low volume processes, so it's very flexible. That's one of the reasons people like machining. And it's capable of various materials. There are very few materials that can't handle some type of a machining process. So there it is, it lands as a secondary process. it certainly isn't a primary, and it certainly isn't one of the tertiary processes which just do finishing operations. But you see there's more to it than just machining here as a secondary process. You also have EDM, injection molding, and additive manufacturing. So I'm going to give you different alternatives to some of these different processes that may still actually be an option for you. So just go a little bit over machining. You've got 3 basic ideas of machining that we talked about here. For those who don't have a long machining background, one is you've got milling, where your tool is actually doing all of the rotating. You got turning, where your part is actually doing the rotating and your tool is stationary. It's actually cutting the geometry. And you got drilling, which is just one of the many hole making processes. It can be done on a drill press, a milling machine, or a turning center lathe, and generate that geometry. And there are certain limitations to a machining process that all of these have in common. So all these have some things in common in spite of how different they are. And one of those is the component is dependent on being fixed in place. It has to be presented to the cutter, and it has to be rotated around, and it can only produce so much geometry at a time. So some of these alternative processes are going to get around that ability to do machining. And there's also limited geometries that you can actually do with machining processes. So there's some limitations behind it. So things that these alternative processes might get you around. So let's look at some of these alternative manufacturing, some of the reasons you might want to go for it. Up here, for various reasons, it might be practical to resort to alternative manufacturing methods to produce some parts. Now, there are no silver bullets. Or very rarely do you get a silver bullet, something where you can say this is going to be the perfect process to eliminate this particular problem. You're typically going to get a trade-off. Like I said before, machining has a lot of benefits. There's a lot of reasons that people like machining, but it does have its limitations. You've got to evaluate whether those trade-offs are actually worth it. A lot of these processes are driven, the benefit might be the volume that they're capable of, or they might be the drawback to them. They might have certain material requirements, or they might have more flexibility. And they may actually either require or reduce the need for specialized skill. The manufacturing facility I gave you before, you have machining skills there, and others you got to take into account that there's going to be a training and a learning curve, which may be worth it, may not be. But again, that goes back to the whole concept of trade-offs. All right, so there are going to be trade-offs. So let's look at our first process, and that is metal casting. Now, you don't oftentimes think of metal casting as a secondary process, even though it is a way to get net-shaped parts and able to, eliminate a whole lot of the issues that go with primary processes. So, give a brief definition. It is simply pouring of molten metal into a mold to form your geometries. So you can see it's one of the oldest processes. That's a crucible pouring molten metal into a mold. Creating whatever component they're trying to create. The entire process is fairly simple. You've got molten metal going into a sprue. The sprue goes into a well or a choke, goes through the gates and running system to a mold cavity with a core if you're trying to create a hollow part, and you've got a riser. And the mold is made up of a cope, the upper portion, and a drag, the outer portion, and typically a flask. This is the generic and very basic metal casting process, but there are more to them than this. You have die casting, investment casting, sand casting, and in a lot of cases lost foam. And in a lot of manufacturing and mechanical schools, you will probably have done this one, these last two, just to learn the processes. But these are some that I've picked for a reason, because they are so extreme in why you would apply them. And I want to give an example of all of these three, or show you some comparison between these three. So this is a table. It comes from a very common engineering textbook, Manufacturing Engineering and Technology, the 7th edition, from Kabakajan and Schmidt. And some of the processes, you can see they are listed as the different types of manufacturing processes or casting processes and their advantages and disadvantages. So your advantages and disadvantages, and comparing just those three. So sand casting, investment casting, and die casting. If we look at sand casting, the shape is not an issue. Weight is very inexpensive, but some of the downsides, they tend to not have very good surface finish. So you are going to have some machining done afterwards. Tend to be relatively coarse and not very precise, so wide tolerances. Compare this to investment casting. You tend to get very intricate parts and shapes, excellent surface finishes, very accurate, precise parts, and a wide range of materials can be used. However, your sizes are limited, it's very expensive, and they're very labor intensive. There's like 9 stages to an investment casting process. Then you've got die casting. Again, very good tolerances, very good dimensional accuracy, very good surface finish, and very high volume. Unlike sand casting, very high volume, but very high upfront cost in designing a die. Part size is limited, and it does have some limitations in the metal, and again, long lead time because of all the design and manufacturing that goes behind that. You can compare this also to some of the characteristics. You can see in sand casting, you've got a very minimal part count, volume count. Investment casting, you can't get a whole lot out, but again, high volume in die casting. Look at the tolerances, 1/4 of a millimeter. This is actually a machining tolerance for these two. Again, in terms of materials, types of materials you can cast, very flexible, but low volume. And this one is a lot more limited, but high volume. So there are trade-offs again. So these are some of the trade-offs that you might have. So if you choose a die casting process, you can actually end up with a completed part, or a relatively completed part with minimum finishing. But you've got to consider there's going to be some, maybe some outsourcing that's going to take place, or you're going to turn your factory into a foundry, and you're going to have to do some follow-up machining if your surface finishes aren't correct, as well as getting some of your tolerances correct. Another process is injection molding. Now this is one that everybody's been touched by this. If you've worked with any or touched any kind of polymer, your toothbrush, most of the things in your kitchen, most of the components in the interior of your car, of your automobile, are injection molded. So a polymer material is heated until it's pliable, and then it's injection molded into a mold, much like in casting, to form your geometry. And that it really does have a lot of similarities to metal casting. Only it doesn't have the entire gating system that a metal casting would have, and obviously it's plastic, and as the name implies, it's injected into the mold cavity. Again, some of the applications, interior automotive parts, toys, Tupperware, combs, hair products, hair care products, toothbrushes. So it has a wide variety of components that can be made through this process. So very, very versatile. Now the process itself, again, you can see this is just a schematic or a GIF of injection molding. Typically the pellets that form the polymer are put into a hopper. There is an auger system where the pellets are entered. It is heated. There's a heating process, so this is brought up to the point where it's actually pliable as it goes through this auger, this giant corkscrew. And then you've got a mold, very similar to die casting, that actually injects the polymer and forms your component, and it is ejected from the mold as a finished part. So as you can guess, this is a very expensive, high overhead process, but once you've made that initial investment, you can crank the parts out fairly quickly with very little finishing process required. And there is a wide range of polymers, so the hardness, the strength of the material, you can get a wide range of properties from this process. Now then there's one called electrical discharge. Now there's two types. There's electrical discharge with an electrode, electrical discharge with a wire. Often called an EDM, electrical discharge machine. As you can the definition, you get a desired shape generated into your workpiece using an electrode or a wire while submerged in a dielectric liquid medium. So it's basically an electrical system that literally burns your part out of metal. You can get very high precision, high surface finishes. So these make very nice components. It's also a relatively low volume, and again, very expensive setup. Also, there's a lot of hazardous materials with this dielectric liquid. There's some special disposal required, special skills in performing this process, and your electrodes tend to be machined in the form of a negative of the component that you're trying to generate. You see this in aerospace, and oftentimes, a lot of times with one-off, maybe even prototype components. So again, just to describe the system, you've got a tank with your dielectric liquid, your workpiece material, and you form a circuit, and your component that you're trying to generate is formed into an electrode, and it burns its shape into the metal that you're trying to get. So, and it is a relatively slow process compared to other operations. Then there's laser cutting, or a plasma cutter. Again, this just uses lasers or plasma cutting to burn or vaporize metal, and to actually melt the metal away. So again, you see this a lot with sheet metal components, sometimes heavier components, but generally you can't do this with very heavy, very thick components. A lot of industrial applications. So some of the pros, again, you get precise cutting, you get very intricate details, but it's a low volume alternative to stamping processes. So a lot of die and stamp and die operations can be an alternative to laser cutting. Some of the cons, you can't really get a lot of 3D parts. There may be some specialization, but that's not typically a laser cutting operation. And you do have some restrictions to part thickness. That laser is not going to be as accurate once you start getting thicker and thicker into your material. So you can see this relative picture, and I want you to pay more attention to this. This is the scurf, or the material is burned away. So this is a lot of your accuracy is being gone, and it's still relatively an accurate process. But just keep in mind that you are literally discarding material out here, all right, as you make your component. Now this is showing a 2D component. It is possible to have 3D features where the head is actually on a knuckle and able to rotate, but again, that's an extremely expensive addition to your components. Now Waterjet, that's something that we have looked at in your project. I think that the process layout actually shows that you're outsourcing for your component, that you're actually redesigning and applying your DFMA principles to. So just a little more depth into it. You're using high pressure water jets, again infused with an abrasive. So this isn't just water, this is water with a grit added to it for an abrasion, and it generates your desired geometry. So it's, you can think of it like laser jetting or plasma cutting with water. Very similar principles. Again, very accurate, and it's got a fine grit in it, so you do get a nice finish out of it. You're able to generate a profile, but you're able to do it through relatively thick material, much thicker than you can with plasma cutters, and there's not a lot of waste involved. The waste that you get from, say, a machining process is much larger than you can with a water jet process. But again, there's trade-offs. Again, typically two-dimensional. There are some three-dimensional applications, but again, those are rare. Whereas machining, you can do a lot more. And even though it can be done thick, it's still, in some applications, there's loss of accuracy. So limitations on your part thickness. And this can be used, again, a wide range of materials: metal, ceramics, sheet metal, so it's a range of materials, even some sort of polymers, and composite materials can be done with a water jet. Now, this one I saved to last because it's got a wide range, and it has come along tremendously in the last 10 years, is additive manufacturing. Matter of fact, I'm calling it additive manufacturing and not 3D printing for a reason. I prefer this because I like it. It's much more rudimentary definition to kind of show the expansion of what additive manufacturing can do and has been able to accomplish in the last year, or excuse me, 10 years. So you're generating a 3D model of your component, okay? And the material is literally added to generate your three-dimensional geometries. So this is no more of a sheet metal process. This is no more, machining one surface at a time. You're actually generating a 3D component as you literally add material. Again, oftentimes still some of the downsides, it has been limited to prototype parts, small manufacturing runs, but even that is changing. Even that is improving. Here's an example. There was a robotic arm, and then for another design, designed for manufacture and assembly application. The machine was actually, or the component was made in separate components and assembled together. And using 3D printing or additive manufacturing, the entire component was made as one single piece. So this eliminated any of the assembly that was required through 3D printing, through 3D printing technology or additive manufacturing. So some of the benefits, you can get very unique geometries. As you can see with a lot of the machining, and particularly in your project, you can saw some of the components, some of the features were being outsourced because a particular operation might not get a certain feature. You can obviously get internal features. There's not a lot of waste because you're actually building. You're not taking material away. So there's no chips, there's no swarf. You reduce the assembly time by consolidating the components. And parts can be generated in an aligned state. So if you have parts that have to be assembled with a certain parallelism, certain GD&T behind them, you can actually generate them already in place. Generate them already in their proper state. Some of the downsides, again, it can be restrictive, and for high volume runs. Depending on what you're doing, your accuracy can be limited. And I'm going to show you there are some instances where they don't get a really good surface finish. Whether depending on the orientation of the component, and the surface finish can be inconsistent. So again, that depends on, to some degree, the orientation of the component. But again, I'm talking about a very broad range right now. Let's look at some specific additive manufacturing. One, the most obvious, the one that everybody thinks of first, is 3D printing. So you've got a polymer that you're building from the ground up and generating a component. Again, you're using typically a wire strands, and what you can do is you can make a lot of really interesting things. I believe this was made as one piece. This was generated as one component here. Even all of the joints were generated as one component. So highly flexible. And you do all sorts of prototypes, very low cost ability to make prototypes of this sort of technique. This is another process known as wood polymer composite. So this is actually wood and a binder combined together to do 3D printing. And this is one of the older processes. The first one I've seen when I'm thinking of 3D printing or additive manufacturing. Again, you're processing, a raw material, like I said, wood and polymer binder. It's heated up, and you create, rough component parts. I saw this in the automotive industry probably 20, 25 years ago. It's still around, because it's a very cheap, relatively fast process. Now this one is a fairly new, as far as the case study I'm going to show you, and it's 3D printing with ceramic material. So again, the same concept of adding material to form your geometries. Now you can see the size of this. It's pretty impressive. This man here is surrounded by the part that he's actually generating. So this is actually being produced. You can see it's got the same sleeve around it. So it's actually producing your component as you go along, and actually generated a 12,000 square foot mansion. This was in China, and it actually was made to create affordable living or affordable housing. So again, very versatile part, but again, as you can understand or probably suspect, this is some very expensive equipment, very large scale equipment, even though this whole thing was completed in one day. Now this is another one that a lot of people are probably more familiar with, which is just liquid metal deposition. Again, you're just taking a powdered metal, and as you build it up, it's almost like weld that you're building a component, and this does require some machining and finishing. This, since it's done in various layers, you're not going to get a really pretty surface finish. As you can see here, it's being built up, but you can finish it. It does require some sort of finishing operations, grinding operations, and some minor machining operations, and you can get a nice surface finish, but it does essentially add in another process to get the surface finish that you like. And then there's direct laser metal sintering. And what you're doing here is you've got your powdered metal and again a laser, and you're building your part from the ground up as you create each layer one by one at a time. And the laser knocks off any of the added material, centers, and then goes through the step-by-step process until you built your component. So the workpiece is created from the ground up, and your platform is actually dropping down stage by stage. As the powder metal goes up, you got a wiper that puts more powder, and the laser centers it on, creating more material and creating a bit more geometry as you go up. Again, the surface is dependent on the orientation. So certain orientations are going to get better surface finishes than others. So from the bottom, you actually see a very rough surface finish, and versus say from the top or the sides where it starts to improve a bit. You also have to have some structural material in order to support this, certain features as you build up. So some questions I want you to take into account as you consider the rest of your project, or just after watching this video. So what trade-offs would you be willing to make in terms of design for manufacture and assembly for a different type of manufacturing process? What are you actually trying to get rid of? What burden of manufacturing are you trying to preserve or take away? Does the expected volume justify your overhead? So what type of overhead are you going to expect if you introduce a new process that you say, well, I'm going to eliminate this machining process or this grinding process? Will your volume, the number of parts you're going to make for pay for itself? And is the geometry, surface finish, or tolerance too important to change? In other words, are you going to, you might be able to get that geometry you're looking for with these new or an alternative process, but is that really worth it, the cost of that process, versus say just designing it so you eliminate that to begin with? Again, it may be something so crucial that you can't change it. It may be something that you don't want to change, or that the customer just demands. But again, another question just to ask yourself, much like with this class, concurrent engineering in general, it's more about finding out what the stakeholder wants, what you can trade away, and what you are required to keep. Again, this is Professor Cummings, and hope this video helps. Hopefully it'll inspire you to do a little more research into different processes that may actually help you out, may actually be more interesting, or just more beneficial in your final project. And again, thanks for watching.